In this video, we're going to look at MRI in 2 dimensions. And the sample we're going to use is that same 2-tube water sample that we saw in the 1-dimensional experiment. But in this case, we're going to be imaging in 2 dimensions, one along the vertical axis here, the z-axis, and one transverse to the sample along the y-axis. And what that means is that in terms of the x-axis, we'll simply be projecting the intensity along that direction. What we would expect to see in a 2-dimensional imaging experiment like that is essentially 2 circles representing the 2 tubes of water. When we acquire our signal in magnetic resonance imaging, we do so in reciprocal space, in that K-space, which we then Fourier transform to get the real space of our image. And we acquire that signal one line of K-space at a time. What we're going to see now is a speeded up version of an experiment that should take about 4 minutes, and we're going to run it through in about 2 seconds. And what we'll see here is an acquisition of a single line of K-space at a time, starting at the centre and moving backwards and forwards, filling up this matrix on the left-hand panel. There are going to be 16 lines of K-space, and each one will have 32 data points across it. So here we go. There we see the signal coming up as separate lines of K-space in the left-hand panel, and as we go, we Fourier transform to obtain the image on the right. Now we've completed the full 16 lines of K-space, and on the right-hand side, you can see the image, which looks a little bit like 2 tubes of water. It's not a very good image, but of course that's because we've used so few pixels. Remember, 16 lines of K-space, each with 32 data points, and in the real space, the Fourier transform of the K-space data, again, 16 lines in this direction and 32 points in that direction. Notice that the orientation of the 2 tubes is a little odd. We really had the sample like this, but what we're representing on the screen is our z-axis along this direction and our y-axis along that direction. We can choose to orient our axes on the screen as ever we wish. Now we could make a better image if only we had more pixels. So what I'm going to show you now is the result of running an image with 64 lines of K-space and 64 data points, a 64 by 64 array. And there it is. It's a much better looking image. Of course, it takes a little longer to get an image like that with more lines of K-space, but you can see it really is a beautiful representation of the 2 tubes of water with these 2 very clear circles here representing the intensity of the water in those tubes. The really important thing in understanding magnetic resonance imaging is the idea of a traverse through K-space. And in the example of a 2-dimensional imaging experiment we've just carried out, we did so on a Cartesian grid where we traversed the Y and the Z-axes. Now we're going to do 2-dimensional MRI in a different way using a polar axis system. Let me explain what I mean using the original sample. What we're going to do here is to apply a gradient in a direction which will be stepped in orientation, so that as we go in our traverse through K-space, we'll get a series of lines acquired on a polar axis system. In other words, with a radial direction and an azimuthal direction. Of course, what that means is that when we come to Fourier transform, we have to Fourier transform the data in a polar manner, not in a Cartesian manner. And that's called a filtered back projection. Actually, the idea of filtered back projection is a very old one, and it goes back to the very early days of imaging. In fact, X-ray CT is done using filtered back projection in a very natural way. So what I'm going to do here is to show you a set of data which we've already acquired on the polar axis system, and then we're going to carry out the filtered projection in real time. We'll see that run in a moment. It may look like it's on a Cartesian grid, but it really was acquired in polar coordinates. So let me run it. There's the completed projection. And again, we see 2 tubes of water. This was obtained using 32 by 32 pixels, but we've actually added a few more pixels in there just to add a bit more resolution in the image. You can see there's some artifacts there. These things out on the side here are known as star artifacts, and they probably arise from some small off-resonance signal that we picked up in each sweep of K-space. So there you have it, the same 2 tubes of water imaged not with a Cartesian process, but with a polar acquisition and the use of the filtered back projection. It's still MRI, it's just done in a different way.